justo en, justo en el ejercicio 5 me parece que era, en el que añadíamos la perturbación al sistema.
¿Sí?
Cuando nosotros hablamos de una perturbación, ¿no se supone que la energía debe ser menor a la del propio sistema?
Eh, menor a la del al sistema no perturbado, dices tú.
Sí, 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 exacto.
No necesariamente, porque acuérdate que vamos a ver, por ejemplo, próximamente ese ejemplo en segunda cuantificación, cuando una interacción puede atrapar una partícula. Por ejemplo, si tú tienes una partícula que tiene una cierta energía cinética y el ambiente que la rodea, que por ejemplo pueden ser deformaciones en una red, pueden atrapar la partícula. Entonces atrapan la partícula, primero la
Ya.
confinan y después su energía puede bajar con respecto a la de la partícula libre, de manera que no necesariamente tienen que aumentar la energía. Fíjate también que el término de intercambio en el gas de electrones también reduce la energía, no la aumenta como el término de el renacuajo, el tadpole. Entonces, fíjate que esos
Ujú.
signos pueden ser positivos o negativos, puede bajarla o subirla. Lo que sí tienes razón es que el término, el H0, debe ser relativamente más grande como término energético que la perturbación, ¿ves? Entonces, la energía puede bajar un poco
Sí.
respecto a ese, pero no puede ser comparable con la energía asociada al hamiltoniano cero, ¿ok? Eso
Sí,
sí.
a eso me iba, porque justo en ese ejercicio se supone que era la energía al cuadrado.
Correcto.
Entonces ahí sí me quedó un poco la duda, porque
Claro, pero
es que ya es
fíjate,
más grande,
claro, pero
no sé.
pues, el asunto es que entonces, claro, es un ejemplo un poco artificial, un poco más artificial que el que hicimos en clase, porque todo el asunto es que, ok, uno lo llama generalmente una perturbación si lo vas a tratar con teoría de perturbaciones, pero aquí como puedes diagonalizar exactamente con la
Sí.
interacción, no importa el tamaño, ¿ves? Entonces no hay contradicción. Si lo hubiéramos usado en una teoría de perturbaciones, claro, ya no se puede considerar perturbación. Entonces, ese sería el problema. Y la otra cosa es que generalmente uno escoge interacciones que no conmuten con el hamiltoniano, con el H0. Este,
Ya.
de manera que entonces, generalmente, si no, tú lo puedes diagonalizar directo si conmutaran con el hamiltoniano cero y no tienes que hacer ninguna teoría de perturbaciones. ¿Ves?
Mm, ya, ya.
¿Se entiende?
Sí,
Perfecto.
ya, profe, gracias.
Buenas tardes, los que llegaron, recién llegaron.
Buenas tardes, profe.
Buenas tardes, profe.
Buenas tardes, si tienen preguntas, dudas, alguna cosa antes de empezar la clase con respecto a la clase y otros temas que les interesen también, es un buen momento ahora. Mientras llegan, esperamos 5 minutos para su compañero. Bueno, so let's begin. Let us share here the okay, so let us sort of review briefly the results of the last class. So remember that we were calculating the corrected energy prime, and we had the following expression. So we have just the free particle energy, which is the first approximation, and then we had an expression which involved the volume, then the integral below the Fermi energy, okay, dl cubed over 2 pi. And then we had this combination of the tadpole, KL, KL, minus KL, LK. Okay, so this was the Hartree-Fock correction to the energy, okay? And this was the tadpole contribution, which was this. And the oyster contribution, which was this contribution here. Okay, so we had this internal variable L, okay? And we needed to calculate those. So we calculated those, the expressions for both of these terms, okay? So this is the Fourier transform of the interaction. So we obtained that the generic KLMN interaction was of the form 4 pi, okay, V0 A squared O cubed. Okay, and delta K plus L okay, n plus n. And this was divided by omega, and then we had 1 plus. Okay, so this was a generic expression. And recall that we had introduced this A through a Yukawa potential. So this is really the solution for the Yukawa potential, where the potential was of this form here. E to the B0A e to the minus r minus RT r prime A divided by this power r minus r prime to the first power. Okay, so this is Yukawa potential. We told you used a lot for models in nuclear physics, but it's equally useful in condensed matter physics, okay? And then we obtained the tadpole, okay? The tadpole. So this was this first term where we have B, KL, KL. We obtained that limit, and that limit was simply setting K equals to M, so it's 4 pi V0 A cubed, okay? Over omega. Okay, and then we have the oyster, which is what was the Okay, LLK. Okay, so, and this, in this case, it was very similar to the previous one, the generic case. Okay, over omega 1 plus k minus n. Okay, so these are the two results, okay, that we obtained. Let's see what, okay. So notice, so one thing we should clarify is how to obtain the Coulomb limit from this expression. Okay, so remember that the Coulomb limit, and this is what we need to show here, the Coulomb limit is taken so that V0 times A, okay, when A goes to infinity, is equal to the square of the charge. Okay, so this means that as A goes to infinity, V0 has to go at least as 1 over A times E squared. Okay, so that they both cancel. Okay, so this is just the statement of what is going on. So if you take that limit, then this goes to, A goes to infinity, this goes to 1, and this goes to E squared, so that makes for the Coulomb potential. This we have to clarify here, because then when we take that limit in more complicated expressions, then it's important to understand what is the result. Okay, so that's a Coulomb limit. Okay, so those are the results that we had obtained. So we can do, there's still one integral left, which is this integral. We have these two expressions here, and we can do, for example, the first integral very easily, okay? So let me just illustrate the first integral. The second integral is going to be more complicated, so we're going to dedicate a session to that, but if we integrate now omega times the integral L smaller than kf dl cubed over 2 pi. Okay, many of the difficulties of this, of doing perturbation theory is that you have to do these integrals at some point, okay? And each of these integrals has its tricks. So one of the first things, for example, that Feynman did with these diagrammatics was write a single paper which contained all the possible integrals that could arise in perturbation theory. So now people could do their diagrammatics, just identify these integrals and just write the equation down. But it's good, you know, it's a training to do some of these integrals completely, okay? So we want to do now this, the tadpole integral, okay? So this is really easy because the tadpole is just, this is just a constant, so we can take that constant out, okay? So let's take the 2 pi cubed out, okay? And then take the equation that we just derived, so it's 4 pi v0, okay, times a cubed, okay, over omega. And then we have just the integral cubed over without anything, because we took the 2 pi already, for L smaller than kf. Okay, so this is a really easy integral here. We can cancel the factors of omega here, okay? And we have 8 pi cubed, so we get 1 over 2 pi squared, okay? Then we have V0 times A cubed, okay? And what is this integral here? This is the integral over all the volume in phase space, in the reciprocal space, always that we have here. So this is a three-dimensional integral of a sphere. Okay, so this should give us just 4/3 of pi times kf cubed. Okay, you can do that integral explicitly. This is just put this in polar coordinates. Okay, and you can do that integral. You obtain exactly this factor, which is simply the integration, the uniform integration, isotopic integration of the sphere. Okay, and this is just the integral of the free particle. So we have kx, ky, kz. Okay, and we integrate until the radius of this, right, is kf. Okay, so clearly this is just the integral. The only restriction is the radius. So we integrate isotropically until a particular radius. So we get this. But you can do this integral. Okay, write this as an integral in spherical coordinates, and just do this integral. We can do it if any of you have any problem with this. We can do it explicitly. But it's very intuitive that this is what it's going to give, okay? So let's simplify this. So we get a 2 here. We simplify this with another factor in the denominator. What else can we simplify? So this is 2 V0 a cubed, okay? And then we get over 3 pi, okay? So 3 pi, and then we get kf cubed. Okay, so this is the first integration. It's very simple. In fact, we will see that when we see the electron gas, which is going to be later in this class, we will see that this term actually is going to cancel when you consider both the positive background in an electron gas, which is a positive background you would have in a solid, and then when you also take into account the interaction between the background and the electrons, those two cancel with this term. So in the electron gas, it doesn't matter. This is just a constant term, okay? And the other term is more complicated, so I'll just write down what we ended up doing in the last class. So okay, second oyster, let me call it oyster term. Okay, in recitation class, that means exercise class. This sounded, the first time I heard when I was a graduate student in the US, the first time I heard this term recitation, I thought they were going to make me sing or something. Okay, so the oyster term, then we have, it's going to give, okay, so I won't write it down here. I just write the full expression for the energy. So we have the energy prime is going to be equal to, just rewriting all these things, B0, a to the 5th, okay, times kf to the 5th. This is part of the oyster term. Okay, over 5 pi. And then you get, I'm putting together the free term plus 2v0 a to the 5 kf cubed h squared over 3 pi. Okay, so this will be the full expression that we have. So I join together all the terms that were k squared in this case. Okay, and so you get this contribution here. So this is a constant, a shift in the energies, okay, a shift in the energy with respect to the free energy, okay, and then you get another contribution here, order of k squared. So this is what I'm going to map onto this expression, okay, and just by matching, okay, match, okay, these two expressions, and matching those two expressions, we get that 1 over m effective mass is going to be 1 over the previous m plus 4v0 a to the 5th kf cubed over 3 pi. Okay, so just solving for the effective mass, you get the expression that follows here. Okay, for m v0 a to the 5 kf cubed over 3 pi. Okay, this expression is really important here because you see that, remember that the Coulomb limit, okay, is when a goes to infinity, okay, then v0a goes to e squared. But then if you have something like this, v0 a to the 5, then this is equal to v0 times a to the 4th. So this is e squared times a to the 4th, and this goes to infinity. Okay, this goes to infinity, this diverges then in that limit, and then this implies that, okay, the effective mass is equal to 0. Okay, so this does not work, okay? This does not work in Coulomb limit. Okay, so this is a very important conclusion because then it says that the Hartree-Fock works well, okay? Hartree-Fock works well, okay? Hartree-Fock works well for potentials with short range. Okay, this is a very important concept for you to understand as physicists, what I mean by short range, okay? I expect that many of you already know, but remember that what does it mean to have short range? Okay, it means that you have in the potential, there's a built-in length scale, okay? Built-in length scale. When there's no built-in length scale, then you have an infinite range potential, okay? So why does the Yukawa potential have a built-in length scale? Because you have a factor, okay? In the Yukawa case, you have a factor like this. And the built-in, you know that this has units of distance, so you've put in a length scale with this A. This is the length scale. Okay? So the Yukawa potential has a length scale. Beyond A, the Yukawa potential decays 1/e of its original magnitude within A, okay? So this decays very rapidly, okay? Yukawa decays exponentially, okay? And this implies a length scale, which is A. Well, if you have the Coulomb, Coulomb has no length scale, okay? This is R, okay? Coulomb has no length scale. So this means that it decays very long, okay? Very long tails, and no characteristic distance for decay. Okay, so this is a power law, okay, like we learned in mathematical methods. This is a power law, okay, and power laws do not have a characteristic length scale. So Hartree-Fock works very well here when you have length scales built in, okay, Hartree-Fock, but they diverge here. Hartree-Fock diverges. Okay, divergence means that it gives nonsensical results. So it cannot be that you have a zero mass for this problem. Okay, this means that that the electrons disappeared essentially from the problem. So this doesn't make any sense, and it's because of this long range interaction. The thing is, and this is why we put the example of the Yukawa potential, is that okay, the M, okay, should be greater than 0. Okay, so where does the length scale come from? The argument is that the Yukawa potential is actually the correct potential, but we have put in, okay, so let me put that, the Yukawa potential is correct. But we need to calculate, to compute A, okay? A cannot just be a parameter I introduced by hand, but it has to be calculated within the theory. Okay, so we should be able to compute it within the theory. Okay, so that's really what remains to be done in this context. Okay, so let's see what we're going to do. Okay, so let's follow the following path. So I'm going to show you, okay? Let's see how it's done. Okay, and this is really an amazing story how people arrived this, because many people were trying to make sense. Okay, already this diagrammatic theory had made a lot of sense in the context of quantum electrodynamics. So people were trying to apply it to condensed matter physics and nuclear physics, and the people were trying to understand what was coming from the calculation. So actually what we're going to see now is something that arose from the point of view of diagrammatics, and it was for a long time, until the 60s, late 60s, it was really controversial, which is the RPA approximation. This is how you go beyond RPA approximation, how you go beyond the Hartree-Fock theory. Okay, and you will be amazed by the fact that this was done first diagrammatically and then translated into equations and then found to be correct. Okay, and this is basically what you do with some other bag of tricks that you have numerically, but what essentially is done in the packages you hear about, for example, VASP. You've heard about VASP or GPAO. Okay, that numerical people do, computational physicists use. These are maybe the most famous ones in the context of condensed matter physics. Well, they use this RPA approximation plus various other effects that you can introduce into the solid in order to explain the behavior of all most of the known materials. Okay, anything you can't explain with this, you have to go to some other considerations in order to get the correct answer. It's a matter of frontier physics. Okay. So what's the nature of this RPA approximation? The essential problem of the Hartree-Fock is it doesn't contemplate the correlations between the electron motion or carrier motion and its dressing. Okay, remember that we interpret the effect of the interaction as a dressing of the electron, but the thing is that we see that the electron is moving around. Okay, so it interacts with other electrons and holes. Okay, let's put them like this. And what we need to take into account is the fact that the electron carries this dressing around. It's not just an effective potential, but it's the electron carries. It's, as we know, we always carry our clothes when we move, right? So it carries its dressing with it. Okay, this is called a correlation. That means that if the electron moves, the cloud of charges around it moves with it. Okay, this is what it means by what we mean by a correlation. So if the electron moves, the other charges are going to move along with it. Okay, and the problem is how do you find this contribution in this problem? Okay. The other thing that we're going to consider, so we consider now an electron gas. So to illustrate an electron gas in a solid, okay? So besides the electron gas, we're going to have background charges. Okay, so this is a very different configuration from the, okay? And the electrons then are going to move around, okay, inside the solid. Okay, around these charges. So these are the the electrons here. Okay. Okay, so I will show you in second quantized form that the tadpole, in this case, tadpole cancels. Okay, I will show you shortly after this, but I want to first show you the picture in terms of what's going on with the electron, how to include these correlations in the electron gas. Okay. Okay, let me just put here, will show. Okay. So, what's the RPA expansion? Okay. The RPA is expansion, so if I throw out the tadpole, we're going to have something like this. So we have the propagator. Okay, as always, as a first approximation, it's a simple propagator. If we don't include the tadpole, then we only have the oyster here. Okay, and then we're going to have another diagram that we drew at the beginning of this class, just to work out the conservation of momentum. Okay, and a final propagator here. And then we're going to have other related diagrams, which is again a subseries that we can justify is the dominant set of diagrams. Okay, so now we have an interesting twist here. Okay, and then we continue with the same type of diagrams. Let me just draw one additional one. Let me draw a very long interacting line, and then we have the bubble, and we have another bubble here, and then we have another bubble. Okay, and all these have the arrows there. Okay, and then we could also have other diagrams like this. For example, now putting together two oysters as we had before. Okay, and then we can have, for example, two of these diagrams, one after the other. So we have okay. Plus higher order diagrams. Okay, and then you can have combinations of oysters and this other diagram and so on. Okay, all the possible combinations of this type of diagrams. Okay, with oyster diagrams and combinations of the diagram with itself and this type of combinations of diagrams. So this is the polarization diagrams. This is the name that it's given to them, polarization diagrams. Okay, so one thing that is going to be nice to show in the homework, okay, which is just a pictorial argument like we did given before, okay? And I'll do this once more for the interaction so you will see, but this, again, you can sum up like this, okay? And this gives me the inverse of the propagator minus what is going to be the self-energy. Okay, and these things here are just handles, remember? These are handles, not propagators, okay? So what is this self-energy? Okay, self-energy, as always, in energy corrections. And you're really going to be surprised at the solution of this. This solution is really amazing what you get from here. Okay, so let's write here. So what should be the self-energy, which we can show from the diagrammatic expansion that I showed you before. So this self-energy is going to be equal to the oyster first. Okay, remember we obtained that result in the absence of the tadpole will just be the oyster, but then you get the second order term, that will be the only first order term. Then we get the second order term, which is going to be like this. You write down here the arrow, okay? And then you're going to have your polarization or your electron hole excitation, and then you're going to have the second order, okay, bubble. With its propagator here, okay, and so on, okay? Okay, so you know that from, if you put that in the denominator and expand, you will get a series of all powers of the oyster, all powers of this first polarization diagram, all powers of the second polarization diagram. So you would have, for example, making a square of this, you would get of the first, you will get this type of diagrams. Then making the square of the oyster will be, you will get the double oyster. But then you can get all combinations, all products coming into the series. So you, with this series, okay, in the denominator of this expression here, you will generate all these possible diagrams, okay? You can sort of do this maybe for just the propagator and the oyster. We already did it. Then you can do it for the propagator, the oyster, and the first polarization diagram, and do that series. And then you show that then if you include this type of terms, then you can have these kind of terms and so on, okay? So this is not difficult to prove, okay? But it's just fun with the drawings that we should enjoy doing in the exercises, okay? So what can we do with this? Now we'll do an exercise which is very similar to what we had done before. And this is also in the spirit of, you know, we do this summation of the picture, so that we don't have to do this integral and then do this integral and then do this integral, right? This is very impractical way. So you first do this summation of a infinite subseries of these diagrams. You achieve this relationship here, and then you see that the types of diagrams you have to calculate. Okay, you have to calculate the oyster, you have to calculate this for the polarization diagram, and so on. Okay, so we're going to do one more cycle. Okay, one more cycle of this same trick, and we'll reduce it to an even smaller set. Okay, so this is the interesting part. So notice that again, this is algebra, right? This is algebraic. So all the pieces of this diagram, okay, are going to be separable, okay? So specifically, we can extract from here a single propagator. So let's put the propagator here, which will be, in the first case, this propagator here, the second case, this propagator here, in the third case, this propagator here, and so on, okay? So this will be multiplied by the interaction line plus, okay? And now notice how I'm going to draw the second driver. So if I draw it like this, we have the bubble, and it goes down like this, right? But to suggest the generic term, I'm going to swap this line. I'm going to move it up like this. So I'm going to draw this diagram like this. Okay, so just swap this line up, okay? And then we're going to do the same. We extracted this propagator, and now we're going to have the interaction line, okay, the bubble. And now we have another interaction line. We're going to draw it up, the bubble, and then another interaction line. Okay, so now you see more clearly what the pattern arising is. Okay, thus higher order terms. Okay, you see this? So notice that the correction to the self-energy, this is in the denominator of the new full propagator, has this type of expansion here. So notice how we're going to see this. And this is a, you know, maybe one of the most important exercises people learn to do after quantum electrodynamics was doing these summations of diagrammatics, okay? So notice what we're going to be able to do here. Maybe that line there is horrible. Okay, so this guy here, we're going to call the effective, what we used to call the effective potential is going to be the new effective potential. Okay, so this new effective potential, and then we draw it nicely here. We're going to draw it like this. Okay, and this effective potential is going to be the old potential, which we know perfectly. This will be, for example, the Coulomb interaction. And then it's going to be this expansion here. So, and notice this, now this interaction is a combination of two simple interactions, but there's a particle hole bubble coming out. Okay, and then you have the next term here. Let's put it over here so we don't interfere. Bubble. Okay, plus higher order terms. So what does this really mean? Now you see that this is a simple interaction, okay, simple. But then we have an interaction, then there's a particle hole in the middle, and then interaction again. So you can imagine, for example, doing here what the physical interpretation of this is. We have this bubble here. So we have, for example, an electron coming in here, okay, and going out. So an electron interacts, creating a particle hole pair, and this particle hole pair now interacts with another electron, okay, that's coming out here. Okay, so this becomes now an effective, okay, so let's put here an effective interaction between an electron here and an electron here. Okay, this is, you know, the exquisite name for this is renormalized interaction, or dressed interaction. Okay, And the dress interaction, you dress it like this. Now you put particle hole excitation in the middle of the interaction, and you get this effective interaction. So again, you have to sum over all possible diagrams there, okay? So we're going to do that in a short while, okay? So, but this is the idea, okay? Let's do that. Let's try to do that immediately. Let's see here. So if you have the, let's see. So, right. Okay, so let's see here how we would sum up that interaction, right? To see how we reduce the amount of work to the minimal expression by summing first diagrammatically. So what we're going to do here is we're going to extract, let's say, a common factor, a single factor of this interaction. So we have the interaction here, we have the interaction here, and we have this interaction here. And let's see what we're left with. Okay? And notice that everything has been done until now, only drawing. So this will be 1 plus, and then we just have the bottom one here on the bubble. Okay? Plus, now we have the interaction, the bubble, the interaction, the bubble. Okay? And so on. Okay? We just took away the interaction that was here, we took away the interaction that was here, and the interaction that was here. And now you can do exactly the same procedure again. Okay, so we have the interaction, and this gives us 1 over 1 minus. Okay? Did you find this interesting? So now you would just have to calculate this remaining diagram. Let's see if I'm not mistaken with this result. I'm not missing any propagators or anything. Let's see. Yes, perfect. Okay. So this instead, notice that this is going to be now the effective interaction, but in the RPA approximation. Okay, so notice that this is going to be a renormalization or a dressing of the interaction. This used to be, for example, this used to be just, this was the bare interaction that comes into the Hartree-Fock term, but now this interaction gets renormalized by these contributions here. So now this is the interaction divided by 1 minus this diagram here. So if we calculate this guy, okay, we compute this guy, and we have our new potential, okay? Okay, and arrive at new correlated potential. Okay, and this is a very general a result that it's used, as I told you before, in all these programs, that includes a various sub-series of contributions, okay, that comes from all these diagrams here, either the oyster, okay, I told you that in the case, okay, I should put here, in the case of an electron gas with background charge. Okay, this is basically a solid background charge. Okay, in this case, the Hartree, the tadpole diagram only contributes a constant factor that is cancelled by the background charge. Okay, is this clear? Any questions? You want me to clarify anything in what I talked about? Okay, one more thing that we could say with respect to this pictorial expressions that we have here. Remember that when we wrote the self-energy, okay, this self-energy is this expression here. Remember we took out this propagator from here, okay? So let's suppose we put this propagator back into the expression. And this is going to tell you the form of the potential, right? So we had that the self-energy, okay, the self-energy was going to be this propagator times, okay, this expansion that we have here, okay, the expansion. Okay, that interaction expansion turns out to be of this form. Okay, so we call it, that expansion we call like this. Okay, and that we can reinterpret as a new tadpole, a new oyster, sorry. So notice that all those diagrams, okay, can be written in the form of a new oyster diagram, okay? And so the form of this oyster diagram is going to be the same form as we had for the simple oyster, okay? Remember the simple oyster? So the simple oyster had an expression which was of the form, okay? This will be now the RPA effective, which was 4 pi e squared over, okay, the q squared, okay, plus 1 over, and let me call it here differently, some lambda. We're going to have a scale, okay? Okay, and whose anti-transform, okay, anti-Fourier transform is going to be exactly the Yukawa potential. And this is in real space, will be the Yukawa potential, 4 pi e squared e to the minus r upon lambda over r. Okay, so this is the whole scenario we're going to have, and in the end, the interaction, the action of all these terms in the expansion, okay, including all these polarization diagrams, and of course we have to have a good reason to say that these are going to be the dominant diagrams in the expansion, okay, give me this self-energy. Okay, that self-energy can be written as an effective tadpole and as an effective oyster, okay? So this self-energy here can be written as an effective oyster, and this oyster, as we implied before, right, has to have the same form of the oyster contribution, okay? And this was a form of the oyster contribution. Remember that we saw that at the beginning of this, right? So this was the oyster contribution. Notice that we have q squared here. This is the momentum times a. So if we take the a outside from here, we'll have a prefactor. And then we have 1 over a squared plus q squared, which is exactly this form, okay? Q squared plus 1 over some length, okay? And then this would be the form of the RPA approximation just by the form of the oyster, okay, in Fourier space. And then the anti-transform gives me the Yukawa potential again. Okay, so this is a very, very interesting, just an argument using only diagrammatics. And this turns out to be completely correct. We haven't done any calculations except for the diagrammatics, but we get exactly what we want. So this is the exercise we want to do. This is the only integral we need to do in this whole process. And I'll show you that this is going to give the following result here. When you have the effective mass, remember that now we can calculate lambda. Lambda is going to come from the calculation of this oyster diagram here. And we're going to get that our effective mass, okay, is going to be just like, very much like the one we obtained for the Hartree-Fock approximation with the Yukawa potential. But now we're going to know there's some slightly different factors coming in here because of the RPA approximation, but it's essentially dependent in the same way. Lambda to the 5, okay. So now we know, if we calculate those, now we know lambda, okay? Now we know lambda. Lambda, I told you already what the meaning of lambda is. Lambda is the screening length. Lambda is the screening length. Okay, and as I told you, the physical scenario, maybe we can repeat it here, is that we have these positive charges, okay, here going around. Okay, this is a crystal in which the electrons are in, and then we have the electrons going around. So if we have a reference electron here, then let's suppose we have other electrons going around before turning on the Coulomb interaction, okay? We turn on the Coulomb interaction and then these electrons are going to be pushed away from the reference electron, okay? And what do we end up with? Well, we end up with the same set of charges here. Okay, we have the reference electron that's going to be solitary. It suffers some social distancing as we do. Okay, all its friends are going away. Okay, they get pushed away by the Coulomb interaction. But now you see that you have here a region, okay, where there is no other negative electric charge. So these positive charges, okay, pluses screen the electron. Okay, this is what screening. This is the phenomenon of screening in the context of the solid state. Okay, screening. Okay. Any questions here?
Yes, teacher.
Yes.
This motion of electrons can cause deformations in the crystal or in solid.
Aha. Okay. So here in this picture, I am just taking into account. I am considering these ions are rigid. Okay. So if these ions are not perturbed by the charges, which is not necessarily true, then this is the picture. But what can happen in the scenario that you mentioned is superconductivity, and we'll mention that later also, okay? Superconductivity is precisely what you mentioned just now. Superconductivity.
Copper pairs.
Right, so the mechanism for Cooper pairing, right? So you have an electron, okay? And you have, for example, your positive charges here, okay? And now the electron comes in here, okay? And what happens? The charges now are attracted to the electron because you know that the crystal is not rigid. So the charges are attracted, so they deform, okay? So they become closer and they create this deformation, which is a piece of an exciton, right? So the electron goes away, this deformation remains for a little bit, and then comes another electron, okay? And the other electron sees all these charges very close together. So there's let me put this other electron here. So now there's an interaction between these two electrons. And let me put it with a red line. Okay. There's an interaction between these two electrons via the lattice. Okay. And this is what we call the Cooper pair. And this turns out to be an attractive interaction. So this is a Cooper pair. So you see how interesting that this same picture just repeats itself in superconductivity.
And why we can only see this effect in superconductivity?
No, actually, I mean, this effect is seen always. The thing is that how do you compare the energy associated with this pairing? Okay, this is why superconductivity only happens below a certain temperature, because the balance between the thermal energy, okay, and the electron-electron interaction, for example, okay, there's an interaction between these two. So the answer to your question is that there's a balance, okay, between, okay, thermal, okay, EE interaction, and electron-phonon, which is this coupling. This is the electron-phonon interaction, okay? And it depends on how strong each of these are, okay? So, for example, in metals where you see superconductivity, this can become the dominant interaction beyond the electron-electron repulsion, which is just the Coulomb interaction or the Yukawa interaction, okay? And the thermal fluctuation. So this is why, for example, different materials exhibit different critical temperatures, okay? So for some materials, you have to lower the temperature a lot. Some other materials, you can just, for example, critical temperatures for superconductivity. So, okay, so you lower enough this thermal effect, okay? The electron interaction is very screened, okay? So this one can become dominant, okay? And you can have, for example, for S-wave superconductivity, for example, you can have 4 Kelvin, okay? Something like this of a transition temperature. But some other materials, you have to lower this to 10 to the minus 3 Kelvin, okay? 3 millikelvin in order to get superconductivity, okay? So this depends on the interplay between these interactions. And that's why you observe superconductivity for some at a relatively high temperature and the superconductivity at a relatively low temperature. For example, if you have a very, very strong electron-electron interaction, you're not going to have superconductivity ever, because other unless you have some other mechanism to screen the electron-electron interaction, okay? So this is sort of the qualitative reason for why you see some superconductivity in some cases and not in other cases. Is that clear?
Yes, teacher, thank you.
Okay. Okay, so let's see what is going on. So let's make the argument for the canceling of tadpole in electron gas in a solid. Okay, this is going to be a really nice exercise in second quantization. Okay, and very simple. So let's not risk. Let's see what we can do here. Let's use some technology to draw a straight line. And we have the red. Ha. Okay, we can make it. Okay, so what was the tadpole? What was the tadpole interaction in second quantized form? Tadpole in second quantization. Okay, so notice that the tadpole is of this form. So you get 1/2 of sum over K and L, okay? VKL, KL, and this CL, CK, CK, CL. Okay, remember that we need to do a swap. I mean, there was this order, but then the operators had a swap inside, right? That to take into account the correct statistics of the fermions. Okay, if you don't remember this, just review the prescriptions we had to formulate second quantized operators. Okay, so we already did this integral here, and this is going to be some constant. So this is going to be V0 over 2. Okay, that Paul did before. Okay, and then we're going to have the sum KL and then CL, CK, CK, CL. Okay, so let's do some operator commutation. So we take out the factor key here, V0 over 2. Then we have the sum, KL, and then we're going to permute. We're going to move this operator here all the way to the C sub L dagger. Okay. So how do we do this? So we permute the first time. Okay. So let me do it so I don't repeat so many times the summation and the V0. So let me do it just here, one line below the other. Okay, so we have here first, and we swap these two, so this produces a -1. Okay, and we get CL, CK. Okay. Okay, now we're going to swap these two. There's just a minus sign here because these two anti-commute. Okay, then we're going to have CL, and then we are going to swap these other two. So I'm going to put the -1 here so we can keep track of everything. And then we permute these two. So this is going to be what? This is going to be this is going to be delta KL minus the swap. Okay, this is just permuting these two here. Okay, so we use the anti-commutation relation. Let me put it here. C A I C J dagger is equal to delta ij. Okay, so we use this anti-commutation relation there. Okay, and then we swap these two, and then we get just the ck on this side. Okay, so this is going to give me two terms. Okay, this is going to give me the term cl dagger, then -1. Let's put the -1 outside. Okay, so this is going to be, let me put the, write it down again. -1. Okay, notice that this is multiplying everything here. So we go to the parentheses, and now we could get the CL dagger, okay, times delta LKL times CK. So let's put here delta KL, okay, and then this multiplied by this. So we get minus, okay, and we get CL dagger, okay, and we get CL, and then we get CK dagger, CK. Okay, that clear? So now we have the summation here. We have two terms. Okay. So the first term is going to be minus here. We got we apply the delta function here, and let's stay with the L index. So we have CL, and then we're going to have a minus sign here, dagger CL, and then we're going to have a plus and the sum over K. And notice that now we can separate these two. Okay, so let me separate it so that we don't generate any conflict. So we have CL, CL. Okay, so one of these sums here I'm going to leave here because it involves CL, and the other sum I'm going to put in here. Beautiful. Okay. So how do we write now this? What is this equal to? This is going to be just the sum over all particles here with wave vector k. So this is going to be, let's call it n, okay, because this is a number operator, okay? So this will be the number operator here, okay? And this will be, again, the same thing. This is the number operator here, and then this is the same thing, number operator here. Okay, summed over all the states, okay? So the eigenvalue of this is just going to count particles. Okay, eigenvalue from whatever vector, okay, you apply to. This is just going to be V0 over 2, and this is going to be n squared minus n. Okay, or V0 over 2, n times n minus 1. Okay? In the large n limit, for example, we typically dealing with lots of particles, large. Okay, this is just going to be V0 n squared over 2. Okay? Just so you know that we know what this value is. If we write, remember that we know how to calculate V0, so let's just remember what that is. I'm just going to write that. So this is going to be n squared e squared over volume squared. And then we're going to have this double integral. okay? But we don't need to know this expression, okay? And this expression, in fact, may diverge. It's going to diverge, okay? So, but we don't care. We just are taking this, and this is another exciting chapter of particle physics, okay? So how to deal with these divergences and cancel divergences that are equivalent, for example, okay? We don't care about the value, so this is proportional to V0 n squared over 2, okay? And now, remember that we're going to have various contributions. So this is just the electron-electron interaction, contribution from the tadpole, okay? But we have various other terms. So let's see the full Hamiltonian. Okay, the full Hamiltonian would be, okay, so we have we have just the kinetic energy, which we know how to write, which we write like this. Okay, then we have our interaction. Okay. Okay, which it generates all the diagrammatics we've seen until now. Okay, and then we'll have the Hamiltonian of the positive charges plus the electron, okay, positive charges. Okay, so you understand all these, so let me just draw them for clarity. So we have the positive charges. Okay, let me just space. There's a couple of lines here. Okay, and we have the electrons. Okay, going around here. Okay, so we have electron-electron interactions. Okay, then we have charge-charge interactions. Okay, they will give me a certain Coulomb potential. Okay, so this is the positive background here. I have here, so the positive background. This one is taken, described by this one, okay? And then we have the kinetic energy of the electrons, okay? So each electron, let me draw that with a different, okay? And this one, the motion of the electron will be this one, okay? And of all the electrons. And then finally, we have the interaction between the electrons and the positive charge. Let's see what I run out of colors here. See what this looks like. So the electron the electron lattice interaction, okay, which is going to be this one here. Okay, so you see all the sources of the sources of these Hamiltonian terms are coming from the kinetic energy of the electron, which is this term. Then we have the electron-electron interaction, okay, the red one. Then we have the positive background interaction, which is the interaction between the positive charges, okay, and the electron-ion interaction, which is this gray one here. Okay, is this clear? So this is our older term, okay? From here, okay, this is only true, the only part of the electron interaction I'm taking here is the tadpole, okay? Take only tadpole, okay? Because we know we have oysters and we have polarization diagrams, all kinds of things coming from this electron-electron interaction, but here for this approximation here, I'm just taking the tadpole, okay? So let's see the magnitude of the positive background, okay? So the positive background will have exactly the same, okay? Remember that electron-electron interactions in, okay, in the tadpole are going like this. N B0 times n minus 1 over 2, okay? As we have one electron, okay, we have one electron per ion. This is the way the solid is built, right? So the solid has some loose electrons, okay, like for example, the simplest case is an alkali metal. So you have a single electron per ion that goes into the metal, okay, that goes into the electron gas. So now we have also the positive ion interaction, okay, is going to give me exactly the same thing. This is the structure of this is you pick one of the n electrons and then you have n minus electrons to interact with, okay? And so you don't double count, you divide by 2. So let's do this exercise for 3 electrons, for example, okay? If you have 3 electrons, then to calculate the interaction between these 3, you just pick one, and this one can interact with these 2, okay? So this is 3 electrons in total. You can choose the first one from the 3, and then you have 2 electrons with which to interact. Once you've chosen one of the 3, you have 2 electrons, and then you can't double count because you choose each of them once, so you have to divide by 2, okay? No double counting. Okay, so this is the how you build this one, and you will build this one exactly the same. So you have the interaction of between n positive ions. Okay, this is going to give you exactly the same on average. Okay, potential, and it's going to, so that you choose the first ion, and then you have n minus ions, n minus 1 ions. So you have n ways to choose the first ion, and then you have n minus ions with which to interact, and then you don't double count till you get 2. Okay? So what's missing now? We have here the tadpole. I already wrote that. This is the ion-ion interaction. Okay? And then what's left? We have the ion-electron interaction. So this is now the ion-electron interaction. Okay? So what's this remaining one? So remember that these are 2 positive because the electrons repel each other. This is a positive contribution. The ions repel each other. They have equal charges. This is positive. Okay? But now these attract. Okay? So how do we calculate those? We have as many positive charges, and we have n positive charges, and then we have n negative charges here. So this will be the number of positive. Okay, let's put it with this sign: number of positive, number of negative. Okay. Again, this will be typically the electron, the Coulomb interaction. So it's the same magnitude V0. And that's it. Okay, so how many positive ions are there? N. How many negative electrons are there? N. And we get this. And there's one thing missing. They attract. So we get a minus sign. Okay, attractive. Okay, and this is repulsive here. Okay, so good. Now we take the N large, okay? Okay, we have a big electron gas. So these gases, for example, in semiconductors can be 10 to the 15 at least, 10 to the 16, 17. Okay, so this is a very large number. So we have that the contribution from the tadpole, okay, plus the ion-ion plus the ion electron we get. In the large n limit, we have, so 2 times V0 over 2 n squared, okay, plus minus V0 n squared. This is 0. Okay? So you see that here we get, okay, tadpole cancels with, okay, ion, ion, plus ion, plus a ion electron. Okay? Any questions about this? Okay, so you see how we can really now neglect, in the case of the electron gas, we can neglect from here the contribution of the tadpole we didn't include in this RPA expansion because we're taking into account the positive background. Okay, so let me just put that note here. Include positive background, or positive background included, I should say. Positive background included. Okay. Any questions? Okay, so we prove that now here. Yes? No question?
No, nothing.
Okay, okay, good. So with this, let's finish the class here, and next time, then we're going to do we're going to have an exercise class, and we're going to see a variety of integrals that are now going to arise with these diagrams that we're going to have to calculate, namely this diagram here, which is the polarization diagram, calculating this diagram here. Basically, this diagram is going to give us the renormalization of the double bond, okay? And we're going to be able to calculate this renormalized interaction, and then the effective oyster diagram, which is going to give us the effective potential. We're going to see next class a very interesting result, which is another way to summarize this, is that this effective, okay, RPA, okay, is going to lead us to the dielectric function. Okay? The same one that you have, for example, that in a solid, okay, when you have a solid in electromagnetism, remember that when you apply, in general, when you apply an electric field, okay, to a solid, what happens to a solid, if it has different degrees of electron delocalization, what happens is that you're going to get a positive charge, okay, you're going to get a, and on the other end, you're going to get an accumulation of negative charges. Okay, and this polarization tends to cancel the field outside, inside. So you're going to have a field in is going to be a factor of the field out divided by the dielectric constant. Okay, so we're going to derive this function now, but this function is going to be derived including the k and omega dependence. So you have dependence on the frequency and the k vector. So we're going to be able to define that function inside a material. Okay. We make this a little nicer here. Okay, next class. And we're just going to see some complex integration. Okay, and that's going to be the last class in this series. Okay, so we finished with the diagrammatic expansion to see that, as promised, was related to the RPA approximation. Okay, and we're going to have a full problem set on these kind of things. Yet we're going to do a few exercises again with going back to second quantization, relating more second quantization to diagrammatics, so you get a nice close picture of this topic. Okay. Okay. Any questions? No.
No, teacher, thank you.
Any comments? Do you like the class? Do you think anything I should do differently in the class about the form of the exposition or anything like that?
Profe, yo quisiera decir una cosita, no sé si nos puede ayudar en una parte. Yo creo que sería importante o algo que nos ayudaría si nos pondría las partes de las que estamos hablando dentro del libro, porque el libro es súper grande y medio complicado de entenderlo.
Correcto,
entonces,
sí.
Si nos va poniendo qué capítulo, subcapítulo, algo así, quizá nos podría ayudar.
Ok, sí, porque digamos precisamente mi rol es guiarlos a través de la bibliografía, pero sí les voy a hacer una guía, porque también el libro expone estos distintos temas de manera muy dispersa también, ¿no? De repente está tratando un tema y después entonces salta a otro capítulo con otro tema y entonces vamos a hacer eso para la próxima clase. Déjame anotarlo aquí para que quede constancia.
Ya, profe, muchas gracias.
Okay. Very good. Okay. So,
thank you.
Okay, so see you tomorrow then.
Okay, see you.
Okay, bye.
Marilita.